Hello everyone, this is Group 51 from Computer Science Department UCL.
I'm Shuai Yuan.
I'm Wu Zekun.
Today we are going to introduce our single cycle processor. This is the schematic block diagram of our single cycle processor. We will introduce it later. Before that, we're going to run our first program on board, the decimal counter.
So firstly, look at the codes on the Mars, and then after we compile our processors, we're gonna run the code on the programmer. Successful. And then let's look on the board. The program function mainly is just counting from 0 to 9, and then reset to 0. The number will be displayed on the 7-segment display on the board.
So the second program is called the square number calculation display. This is a bit challenging than the previous one. Basically, you can see that the number showed on the 7-segment display is continuously growing up. These numbers have a certain mathematical regularity. As you can see, these are a sequence of square numbers. Note that these numbers are output in hexadecimal form.
Well, the next is the program 2 code. Basically, it can divide it into 4 parts: the 2 loops, initialized, and reset parts. It's basically used the way of plus the odd number of themselves. For example, 2 is 2 plus 2, 3 is 3 plus 3 plus 3, and we have 2 loop acts like a for loop that have an outer and an inner counters. Then output the added value each outer loop. When it reaches the set limit, it will go to the reset stage to reset value and restart program.
Well, let's first introduce the single cycle processors. The single cycle processors mainly have 3 stages to run: the fetch, decode, execute stages. Firstly, let's start with the program counter, which is a 32-bit register. The program counter is used to store the address of the next instruction. The program counter will first give the instruction address to the instruction memory, as well as the ROM in this case. Then, the instruction memory will base on the address to fetch the instruction, and then output the instruction. The fetch stage is finished. Then is the decode stage. When a control unit receives opcode and a function from the ROM, it will decode this into nice signal output, which is used to control the data path. For example, the instruction BEQ, which will decode it as the branch become 1. The decode stage is finished. Then is the execute stage. You look at the register file, which is the fastest part in the processors. It plays the role of storing the temporary data value. Back to our case. It will execute the instruction BEQ. It will compare the value into 2 registers, and then register file will give the value to the ALU, which stands for arithmetic logic units, which can achieve multiple logical and arithmetic calculations. The way it's compared to value is to do the subtraction in the ALU. If subtraction is equal to 0, it will output 1, and the branch is 1. Then, it will base on the previous 0 value and the branch value to decide, and switch the value of PC set to be PC plus 4 plus the bits 16 sign extended and multiplied by 4. Briefly speaking, it will jump to the address we want to go, as well as the INM. Well, if the result is not 0, it will just let PC plus 4 continue the next instruction. Then, the ALU result and the data will store it into data memory, and also will give to our display driver to display on our board as a memory mapped output. Data will send back to the register file. Then, the executed stage is finished. And this is our brief overview of how the single cycle processor works.
Use register. So we start from the SR latch, the basic memory unit, which is an essential part of the register. SR latch have 2 inputs, reset and set, and 2 outputs, Q and Q's complement. So it is a sequential circuit which
the output always depends on the previous output and input. And then we go into the next stage, the delatch. The invention of the delatch is because sometimes there will occur the same case that both the Q and the not Q become one. So we shall become a conflict status. In order to avoid this conflict status, we need to add in a new input, clock. And the delatch is only work when the clock is a rising edge. Then, the next is reset flip-flop. We add up a new input in reset flip-flop, which is the resets input. In our case, when resets is low, it will reset all the contents in the flip-flop. Then, the next is our 4-bit register. We basically use 4 reset flip-flop to build a 4-bit register. And then, it's the 16-bit register. We use 4 4-bit register to build it. And finally, it is our program counter, 32-bit register, constructed by 2 16-bit register.
Next, I will introduce the control unit. The control unit is an essential component for processors, which directs the operation of it. It tells computer arithmetic and logic units, input and output devices, and the memory to respond to the instruction that have been sent to the processor. The control unit is consisting of 2 parts, the main decoder and ALU decoder. Firstly, the main decoder have a 6-bit opcode input, and then it's based on a complicated logic gate, simplified by using K-map to produce 9 signal outputs. And one of these, the ALU opcode, have 2 bits that give it to the ALU decoders, which act the function of decode the ALU function code. So next, we will mention about the ALU decoder. The ALU decoder is based on the ALU opcode 2 bits from the main decoder and the 6 bits from the function code. And then, it will decode the ALU control code that will direct the function of the ALU and send it to the ALU. And what is the control unit done is to control the data paths in the processors and send the signal to each component to direct how they will interact with the whole processor.
Multiplexer, also known as data selector, is a device that selects between 2 different input signals and forwards it to a single output line. Let's look at the 1-bit multiplexer first. According to the diagram, we can see that we have 2 inputs called A and B, and then there's a select input named as S. If S equals to 0, output equals to A. If S equals to 1, output should be identical to B. Then we used 4 1-bit multiplexers to build a 4-bit multiplexer. Then use 8 4-bit multiplexers to build a 32-bit multiplexer. To accommodate special cases in the processor, we also built a 5-bit multiplexer. In this single-cycle processor, we use carry look-ahead adder, CLA for short, to calculate the formula for addition. The carry look-ahead adder calculates 1 or more carry bits before the sum, which reduces the wait time to calculate the result of the larger value bits of the adder. In other words, a CLA improves speed by reducing the amount of the time required to determine carry bits. We firstly build a half adder and then use it to build a full adder. When we give 2 1-bit inputs, we can get the sum output and carry out output. After that, we change the carry out output to generate output and propagate output, which are needed in carry bit calculator. For convenience, we create 8 4-bit CLAs and connect them in ripple carry adder way. When we have CLA and multiplexer, we can build an ALU. ALU is the most important and significant part of a single-cycle processor. With different inputs, ALU can control the processor to execute corresponding commands with different outputs. This association is shown in the table below. In addition, according to the image of ALU, we can see there is a part called comparator. The comparator is a logic switch composed of XNOR gate and AND gate. Its function is to compare two inputs and detect whether they are equal or not. Note that we also have to build a 32-bit comparator. The BDF is a fault mentioned. As you can see that there is a zero output, which detect whether the subtraction of the two input is zero by using comparator. Sign extended can increase the bit of the binary number while retaining its simple and value. This is done by attaching the number to the most important side of the number. For example, if the digit 0001 is represented by 4 digits, and the sign extended increased the word length to 16 digits, the new representation looks like this. If the value of 1101 is represented with 4 digits, the complement of 2 is used. The new representation looked like this. In digital circuit, the shift register is a series of flip-flop with the same clock. In each trigger output connected with the data in the chain of a trigger input, lead to switching circuit of a location stored in bit array. The data input and out of the last point in the array is transferred at the end of each conversation clock input.
Next, I will introduce the display driver. Basically, this display driver is a memory-mapped output device that would display the data in the processor on the board. So firstly, it got 5 inputs. The address inputs, data inputs, clock, reset, and return enable inputs. So, firstly, it will detect the two address, which is FFFF0 and FFFF1, and when the reset line is low in our case, and the return enable is high. When the address is FFFF0, it will first write the data into the 32-bit register, and then display on the 7-segment display. However, if the address changes to the 1, I will also have a rising clock edge on the clock, and also the the low value in the resets, and the high value in the write enable. It will just take the bit 0 of the data bus and store in a single flip-flop, and this flip-flop is just determine whether the segments are switched off, or whether it displays the value in the register. Also, if the return enable is off or is low, it cannot return anything in it, and it will remain the value inside the data bus. Also, if the reset become high, in our case, it will just reset all the value, and it's all become 0. And also, display driver only work when the clock is on a rising edge. Then, it will output on the 7-segment display by 7-segment displayer, and this is about our display driver.
Thank you for watching,
And we appreciate about your teachings.
and it's our great pleasure to be a student because you taught us how to build our first computer.
We'll always remember you because it is an unforgettable memory in our life and in our study of computer science. Love you.
Love you.